morning, everyone. Welcome to the Winter 2016 University of Washington EE Colloquium. I am Arka Majumdar, and today I have the honor of introducing today's speaker, Professor Ali Adibi from Georgia Tech. He's the Director of Bio and Environmental Sensing Technologies and Joseph M. Petit Chair of School of Electrical and Computer Engineering in Georgia Tech. His research group has pioneered several structures in the field of integrated nanophotonics for both information processing and sensing. He is recipient of several very prestigious awards, including Presidential Early Career Awards for Scientists and Engineers, Packard Fellowship, NSF Career, and the SPIE Technology Achievement Award. So please welcome Dr. Adibi.
Good morning, and thank you for the kind introduction. I'm honored and privileged to be here. I'd like to thank ARCA and the organizers for inviting me to be here and talking about some of our work in the area of integrated nanophotonics with the goal of looking into the future of silicon photonics in making practical, reliable, reconfigurable integrated nanophotonic structures. And of course, I'm thankful to a large group of students and postdocs who did the work in my group. I assume the audience is not all experts in optics, so I give a little bit of introduction. The field of silicon photonics has seen a lot of advances in recent years that has made this technology a promising solution for practical applications, coming along with heavy investments from the government and industry, even recently providing a $200 million grant for making manufacturing related centers to realize the silicon photonics systems to the applied world. Some of the advances that has made this possible is the design of high-speed modulators, integration of lasers and detectors on silicon, which inherently is an indirect semiconductor material, and bringing the cost of propagating light down, basically bringing the loss of the waveguides and the resonators down. And with waveguides and resonators being the bread and butter of the integrated photonic structures, these advances has made the formation of high-performance functional devices possible, and some of them are listed here. And there are some niche areas where photonic crystal technology has come along to make life more manageable in this field. Our expertise is the use of resonance-based structures to limit the size and bring the performance measures up. And this is a typical microdisk resonators in silicon structures, 20 micron radius. The thickness of that is usually in the ballpark of 200 to 300 nanometer. And it is coupled to a waveguide. So usually light comes from one side and then couples into the resonator. It stays some time in the resonator and goes back or never goes back, depending on your design. And one of the key advances in recent years is the ability to make these resonators with very large quality factors, which is usually defined in the form of center frequency divided by bandwidth. So very sharp resonances, high quality. And that's one of the earlier results we published with 3 million Q quality factor for such a disk. Well, then some of the problems of these structures with this size is the presence of higher order modes. So if you're dealing with a resonator, you prefer to have only one of these modes, which is a dip in transmission, meaning that the signal that came in went into the resonator, didn't go out. You like to have one of these, not many of these all over the place. And of course, the distance between the adjacent ones that are the same resonance with different factors of 2 pi phase, you want that distance or free spectral range to be as large as possible. And most of the time when you work with bigger structures, light is confined inside the structure, and you have to bring your incoming waveguide very close to that resonator to let them talk, and that makes fabrication problems. So we invested a lot of time in kind of miniaturizing these structures and pushing the limit to as small as possible. And it's known that when you push the dimensions of an optical structure down and down, the field comes out, and higher order modes stop to persist or stop to be present. So this is an example of the electromagnetic field profile of the first order mode and second order mode when you shrink the size of a disk to 1.5 micron, thickness of 200 nanometer, and it's clear that the higher order modes become leaky, go out, so they don't bother you anymore. Also, most of the energy of the first order mode is in the periphery, and if you cut the center, you will get rid of some of the higher order modes. So this way, we could make structures that are single mode over a very large range of wavelengths. This is 70 nanometer, and you get only a single mode. The challenge at the time was to make the quality of fabrication high enough so that you don't get the imperfections at the edges, reducing your quality factor, adding to the loss. And this was the highest quality factor reported for such a small disk. And this is a so-called add-drop architecture. When the signal comes, resonator picks its own resonance out and then sending it in another arm. And again, you will see that you have a single mode operation, in this case with 2 micron radius disk over 57 nanometer. So one of the first thing that comes into the mind is that if I can use a resonator to address a small portion of the spectrum, just like in this case, resonator R1, then I can have an array of these resonators at different wavelengths and then combine them to shape the spectral response of the overall system. So in this case, we have an example of 6 resonators that are coupled to an incoming signal, and then each resonator is responsible in providing the response for a portion of the spectrum, and you get collectively that. And then within each resonator, you can play with the geometry of the resonator to shape that resonance, that specific spectral response. This is one example when you have 2 of these resonators coupled together in order to make, for example, a flat response as shown over here. So now, in essence, you are able to shape a spectral response using very tiny resonators that are all fabricated together and then all coupled to an incoming waveguide. The most natural application that one can think of is a spectrometer, where you have a spectrum that is unknown coming, and your job is to analyze and estimate different contents in different spectral channels. So this is an example of a 90-channel spectrometer that we fabricated. 90 resonators are fabricated here. The size is selected so that the resonances are adjacent to each other. And then a waveguide wraps around the structure in order to talk to all of these structures. And this is the response. As you can see, you will get each resonator selecting a channel of your spectrum and analyzing it. And this is kind of a zoomed version of it. Again, these are in the form of micro donuts. The center is etched in order to avoid higher order modes. And the distance between them avoid crosstalk. Now, I go a little further into the design. And in order for the output of each resonator to come out, we have a waveguide coupled to that. So this is my bus waveguide bringing all the channels. And this resonator picks one of those channels, couples it into this waveguide. And then all of these waveguides come into the central region. And at that, each waveguide is coupled into a so-called scatterer, whose job is just to send the signal out of the chip so that you can monitor it from the top by a camera or by a detector array. And this way, what we do is we have an array of these resonators here and here on the top, and we interleave them so that resonator 1 is here and 2 goes up there, so the crosstalk between them is removed as the resonators next to each other are prone to have the crosstalk. And when I say next to each other, I mean next to each other in frequency or wavelength. So overall, this is the spectrometer, and this is the response of the spectrometer. So we put it into a characterization system. We couple light in, get the light out, and then we use a tunable laser to change the wavelength from one end to the other end of the spectral analysis. And when the wavelength changes, you can see that this brightest spot just sweeps between different regions. That means it's going to different resonators, coming through the waveguide and then coming out. And each one of them is representative of information in one channel of the spectrum. And collectively, you can estimate the spectral response. There's a little bit of reminiscent that seems to be a crosstalk. Just to clarify that, that's because of the saturation of the camera. Now, if you look at the performance, you can get down to 0.1 nanometer resolution over 60 nanometer bandwidth with 0.5 dB insertion loss. Such a spectrometer, if you want to purchase it, is going to be very expensive. And not only is this a simple, tiny system chip, but also it can be made even more attractive by putting your scatterers on top of these disks, so that each disk doesn't send its signal to a waveguide to go to the center. Rather, it just pushes it up. And then there is a kind of a matching stage or micro lenslet array that matches the size to the detector array, and detector array integrated on the top. So you have a very nicely packaged chip that can give you this performance. This technology is now out of my group and being commercialized in a company called Sinura Incorporated. And they're talking to different people who use such a spectrometer in OCT, for example, for eye imaging and so on, and has a lot of potentials for future applications. Now, one of the reasons silicon is so attractive as the optical material, in addition to the availability of the fabrication facilities thanks to electronics, is the ability to reconfigure optical properties of silicon. When I say reconfigure, in the simplest form, you can think of tuning. You have a resonator. By applying a signal, you want to be able to change its resonance wavelength. That's what we call reconfigurable. Now, if you want reconfiguration in any system, especially in optics, these are some of the qualities that you need to get from that. You want it to be CMOS compatible, because you want to eventually manufacture things using the existing CMOS line. And then you want it to be low power. You want it to be a wide tuning range. You don't want to spend a lot of energy and then the tuning range over 1500 nanometer wavelength is 0.0001 nanometer. And of course, you want the tuning to be done fast. You're talking about nanoseconds and picoseconds and femtoseconds and attoseconds and so on eventually. And you want it to be low loss. You don't want to send your light in and get 1% of it out. These are practical requirements. And in silicon, there are different techniques. And that's one of the strengths of silicon. Free carrier plasma dispersion is one technique in which you inject carriers, and the presence of carriers changes the index of refraction of silicon. Thermo-optic effect is a strong property of silicon. You just heat silicon up, it changes its index of refraction. Electro-optic effect, silicon is not electro-optic, meaning that you apply a voltage, it doesn't change its index of refraction much. But if you make trenches or slots inside silicon and fill them with polymers that are electro-optic, you can get that property incorporated. And optomechanical is another technique. And these are kind of an array of devices that have been proposed for reconfiguration of silicon. I just say a few words about the thermal tuning and some of the works we did under DARPA for this. So the idea here is that you have a heater that heats up silicon here. And then this is your silicon resonator. And then the heater is separated from silicon by a buffer oxide. And the reason is that if you put heater on top of silicon where there is electromagnetic energy, then metal causes loss, and all the advantages of high quality will go out. So this is the fabricated device. It's a ring, and then you have nickel chrome as your material for heater, and then you have gold electrodes to apply voltage. And by applying a voltage, just like a resistor, you generate heat, heats up silicon. Of course, it has to go through a silicon dioxide buffer, and since silicon dioxide is not a perfect heat conductor, it's going to give you a latency. It takes some time from application of the signal till silicon gets warmer, and then its index of refraction changes and reconfiguration is done. And this is the resonator. So this shows the transmission through this waveguide here. And of course, the dip in this transmission is the representative of the resonance of the resonator. The signal goes from waveguide to the resonator. And by applying the signal to the heater, you change the resonance wavelength of the resonator. So when we started this work, you were getting microseconds of response time. And in order to solve this problem, what we thought was to put the heater right on top of silicon and make the disk as small as possible. So this is what we developed under that DARPA project. The center of a disk is an immune place because most of the energy of your fundamental mode is in the periphery of the disk. Electromagnetic energy of that mode doesn't get all the way to the center of the disk. That's how the whispering gallery modes are. So the center is immune from loss. So you put the heater right on top of silicon, and then the disk is very small, so you get two advantages. You don't need to go through oxide, and then very soon you get into the periphery and you change the index of refraction in the places that you care about. So this is the theoretical response for a ring. This is impulse response. At best, you get 725 nanosecond. And then for a disk, it's about 25 nanosecond. Again, these are theoretical simulation, doing all the heat equations and optics equations and combining them. So what we did is to fabricate this device and then put the heater's nickel chrome in the center, apply the electrodes, and so on, and then monitored the impulse response, and we got 85 nanoseconds. So it's not as good as the theory suggests because of all the imperfections between theory and experiment. But then important thing is that if you do pulse shaping for the signal you apply for reconfiguration, then you can get into a stable status within 85 nanosecond. So you can reconfigure silicon in 85 nanosecond. And the question that comes is that, OK, but that's a one-time reconfiguration, because if I want to reconfigure it back, I need to cool it down. And I don't have this luxury of making a very small structures to cool it down. So in order to address that, what we usually work with is a so-called differential architecture. So instead of one resonator, we use two resonators. So in this architecture, which is a balanced Mach-Zehnder interferometer with two resonators, if the signal comes and the two resonators have the same properties, then at the end, you will not see any phase differences between them. Now, if you heat up one of the resonators, you can apply a phase to that signal, and that phase will cause into a destructive interference. Now, if you want to reverse that, instead of cooling this down, you heat up the bottom resonator to apply the same phase, and this way you will just bring them back together, and again you will get constructive interference. And that's the experimental data that we demonstrated. This is the leading edge and trailing edge, and as you can tell, both of them are within that 85 nanosecond. Of course, if you want to do 85, 85, 85, 85, at some point the system heats up. But usually in these types of reconfigurations, you don't need to reconfigure the system that fast. Just a few words about power consumption. The size of this microdisk is a very important factor in the power consumption. For 4-micron disk, 265 gigahertz is the frequency change you get per milliwatt. And for 5-micron, this becomes 177 gigahertz. So your power consumption goes high. But one of the parameters that is important is how much power do you need to apply to get a pi phase shift, which is 0.36 milliwatt per pi phase shift, which was the best, again, for its own size. So saying a little more about the practical application of such reconfigurable devices, this was the target of Silicon Phaser project funded by DARPA, where you wanted to have a filter chip which you apply a few electronic signal to it, and you tell it to be bandpass or band reject at a given frequency with a given bandwidth. So completely reconfiguring your filter from the performance issue, from the center wavelength issue, from the bandwidth issue. And the idea is you have a unit cell, and then by making an array of these unit cells, you get the higher and higher and higher order filters. Some of you have taken courses in electronics and are aware of Butterworth and Chebyshev type filters, where you know how a unit cell can be replicated in order to make a complicated system. Usually in designing these, we worked with the poles and zeros of these transfer functions, and then by placing them at the right locations using our optical system, we will get the response. So this is a fourth order filter. This is a unit cell that we have, and this is a second order filter, and this is a second order filter. And it's a combination of resonators and waveguides. That's all we have in integrated optics. We don't have anything else. And this is the response. You can apply the proper signals to these resonators to get a notch response and tune that notch response over a range of wavelengths. And you can apply another set of signals and get a bandpass filter. And that bandpass filter can have a large range of bandwidth. And of course, in this example, you may lose some of your signals, so you have to then compensate that. And then you can change the wavelength in a large range as well. So it's kind of a reconfigurable filter in the sense that you get the package, you apply the controls, and then you get any response technically that you want. And of course, this is just a fourth order. Increasing the number of unit cells will give you higher order filters, sharper filters, and so on. So if silicon is so good, then why do we need other materials? What's the title of this talk? Hybrid material platforms. Well, silicon is good, but it has its own problems. One of the problems is a strong nonlinearity in silicon. Now, some people build their career on nonlinear optics. Well, they're happy with nonlinearity in silicon. But for other people who want to do information processing and filtering, any nonlinearity is a killer. Silicon has limitations in the amount of power that it can handle before it shows nonlinear response, again, because of the high nonlinearity in silicon. And then usually a few hundred of microwatts in a device is something that you would recommend. Silicon has 2-photon absorption. It has free carrier absorption, and it has optical instability at high powers. So if you apply a lot of power, you generate heat because of loss, and that heat will generate, would also generate carrier. So from one side, index of refraction is changed by the heat you generate. From the other side, index of refraction changes by the carriers you generate. And they two compete with each other, and all of a sudden, this very beautiful resonance behavior will turn into a nasty, unstable performance. So that's one of the major issues that silicon has. And of course, there is a solution that people have thought is silicon nitride. Again, we don't want to move away. We don't want to move away from CMOS compatibility because of fabrication. So silicon nitride has 20 times less effective nonlinearity. It doesn't have any free carrier absorption because it has no semiconducting behavior. It's an insulator, so there's no carrier involved. And its loss is also much smaller than silicon. So this is some of the work in silicon nitride we did. If you make a resonator inside the silicon nitride and properly anneal it, you can get quality factors in the ballpark of 6 millions for this disk, which is among the best reported. And then you can go to higher sizes. 60 micron can get 8 million in this example, and 100 micron can get 16 million quality factor. And it's an art of fabrication and material deposition. This is a comparison of our work and other published work. Again, you can get very high quality factors, 16 million, for a disk that is as large as 100 microns. So silicon nitride can give you very high quality factor resonators, which is an indication of a very low loss of silicon nitride. So then, if silicon nitride is so good, why not switch to completely silicon nitride? And the problem is that you cannot reconfigure silicon nitride, because silicon nitride can't accept carrier electrons or holes because of being insulator, so you cannot change an index that way. Its thermo-optic effect is very weak. And then you cannot easily combine it with polymer and apply the voltage to the polymer. So the solution that comes to mind is to integrate silicon and silicon nitride somehow in a vertical integration platform, as shown here or cartoon-wise here, where silicon is used for doing reconfiguration, modulation, tuning, and silicon nitride is used where you need to have very high powers, very low losses, high quality resonators, and so on. And then being able to switch light between the two layers very effectively. So that's the name of the game to make any hybrid material platform. And of course, the good news is you can have a silicon dioxide between the two, thereby controlling this size of this so-called gap between the two layers, you can get the coupling coefficient in a very large range. So by properly designing it, you can couple the two structures very well. So this is an example of a waveguide in silicon coupled into a micro resonator in silicon nitride. And light goes from the waveguide into the resonator, and you get the quality factor in the ballpark of 3 million collectively from the two devices. And you can also make filters by integrating silicon and silicon nitride. In order to make coupling between the two structures practical, you need 90+%, close to 100% hopefully, coupling efficiency between different layers vertically. So there are two solutions that we and others propose. One solution is to use grating. So this is a silicon layer. This is the silicon nitride layer. And the idea is light comes from silicon. Grating sends it up. Grating sucks it in. And then you will go from silicon to silicon nitride. Now, of course, you need to have good designs for these detectors. And then we add 2 layers of reflectors on top and bottom, so that the signal that is not coupled into the silicon nitride layer comes back, and in the second trial goes into the silicon nitride layer. And there is an optimization problem, as you can tell, where you have the sizes of all these gratings and the gap between them and so on as design parameters. And we did that by genetic algorithm. And this is the results of an optimization. So the signal comes from the silicon waveguide, and then it gets into the grating area, and eventually you can couple it into the silicon nitride waveguide. And this is the performance and tolerance analysis. This is the experimental data. So you can see that you have about 10 nanometer or so good bandwidth where you are close to this peak. And then single and double mirrors, of course, change the efficiency and insertion loss. The misalignment in the grating because of fabrication imperfection will have an effect in your performance. But as you can see, the peak is fairly wide, meaning that you can tolerate a good amount of misalignment coming from fabrication imperfection. And then by changing the cladding thickness and buffer thickness, you can also change the performance of this device. This is the actual experimental result. So this is a silicon nitride reference. So we have the waveguides, the 2 waveguides fabricated in the silicon nitride layers, silicon layers, and then one in silicon nitride. That is the architecture. So light goes from silicon nitride, silicon layer into the silicon nitride layer, and we add the top mirror. And this is the performance. This is the normalized transmission as a function of wavelength. And you can see by proper design, you can get the very good quality coupling between the two layers with insertion loss of 2 dB and bandwidth of better than 40 nanometer, which is good for many practical applications. This is just one mirror. If you use 2 mirrors, you can get close to 1 dB insertion loss. Now, material-wise, one of the challenges that we deal with in these integrations is that, well, we have this silicon layer. So this is silicon oxide, and then the bottom is also a silicon layer for support. And then when we look into that, fabrication-wise, we may run into some problems. What is the problem? I need to fabricate my silicon device, and then I need to deposit my silicon nitride to be very high quality. I need to do the deposition using LPCVD at very high temperatures. So that can cause problem to my device. I have to somehow tolerate it. And also, when we design that device, then I need to infiltrate these regions with silicon dioxide and then have a layer of oxide to put nitride on top. That layer has to be very flat. I need to do polishing on that. So these are some of the fabrication challenges that we encounter. And in order to resolve that, we developed a so-called back-end integration, which uses wafer bonding, and that can be done at the wafer scale. So the idea is shown here. You have that silicon, oxide, and support silicon. This is called an SOI, or silicon on insulator. And then we put a layer of oxide on top. In parallel, we have silicon oxide, and then nitride is deposited at high temperature. No fabrication is done yet, so I can put it into a furnace and heat it up, put a layer of oxide, and then invert this and bond these two together. And then after that, I remove the regions where silicon doesn't need to be to fabricate my silicon nitride device, and separately, I fabricate my silicon device. And of course, these layers are etched away. So it's kind of done by bonding, and it took us about a year to get into the sweet spot, because we got a lot of these bubbles when we bond the two layers by pressure bonding. But then we learned that by adding vent channels to remove the unwanted gases, we can make very good quality material on top of each other. In order to couple the lights in this structure over a large range and get a large bandwidth, the second solution we proposed was to use a tapered waveguide. Well, it is well known that if your waveguide is tapered in size, then eventually your signal becomes out of your waveguide, becomes large mode, and then you can couple it into the top layer. So that's the architecture that we proposed. And by using finite difference time domain simulations, we noticed that you can get coupling efficiency very close to 1 over a very large bandwidth. And this is our experimental result shown over here, which give us, over a large range, better than 95%. So this variation is exaggerated by noticing that this is 0.95 and this is 0.97. Over 3% you have this variation. And to show that this idea really works, we made an optical path where you have silicon shown by red, and then silicon dioxide showed by cyan here. So you have a grating. Light comes from the top into the silicon. Silicon is tapered, and light goes into the nitride, coupled into the resonator, comes out of nitride in the top layer silicon by tapering, and then by a grating it comes out. So I have the means of analyzing the whole structure. And this is what we obtain. So you will get very close to 100% transmission between the two layers, and you will see the resonances as well with very good quality. So that shows that there is no problem in coupling light between the two layers and seeing the resonance effect. We are now working on a modulator that I just show some of the initial results on that. So this is a micrograph of this structure. The idea is you have a waveguide that is coupled into a high-quality factor silicon nitride resonator. So this whole portion is in silicon nitride, and light goes into two paths, either goes around the resonator or comes out into a waveguide and couples into a silicon structure, where I can add a phase by applying a heat signal or a p-n junction device, and then comes out, and these two paths combine again. So it's kind of an interferometer. So by applying this phase, you can change the output. You can do modulation. If the two signals add in phase, then you will send the light out into the second waveguide. If out of phase, you don't. And this is the performance that you can get out of this experimentally. So by applying a heat signal, you can have no transmission, minus 20 dB into this structure, all the way back to minus 5 dB transmission. So that's kind of a modulation that is done by taking advantage of the reconfigurable properties of silicon in the silicon layer and the very high quality of silicon nitride. I didn't get into the reason for this architecture, but that has a very clear reason that we are, hopefully soon publishing it. So in addition to that silicon nitride silicon material platform, I would like to talk a little about another hybrid material platform, which is called double-layer silicon. So the idea is that you have two silicon and insulator architectures, substrate, and then you bond them together, and you remove the oxide and the handle silicon layers on top. So you will end up with something like this, where now you have two silicon layers separated by a controlled layer of oxide, and you can make waveguides and resonators in it. So this is a waveguide formed in a double-layer silicon, and you can see the oxide in between, and this is a resonator. And over a couple of years, we were able to bring the quality very high to get very high quality resonators, solving lots of problems in there. This is a 2-micron disk with quality factor of 58,000, again a resonator, and this is 20 micron with quality factor of 600,000. And these are close to what you get in normal days for a silicon and insulator. So getting into 2 layers is not a problem. But what's the big deal about this double-layer structure? Just before going into that, I make a quick comparison of this work and other published works. So this is a transverse magnetic mode, which has most of its energy in the oxide layer, and this is transverse electric mode. And the quality factors are listed here. And really, if you compare them for something in that ballpark size, let's say here is a 5 micron, you get 250,000. This is 40 times larger resonator, which should give you a better quality factor, but still you don't get that. So this clearly means that by using this high quality bonding compared to the other techniques, you are able to get very high quality material. What's the big deal about it? Well, this provides a device, This provides a device technology. The idea, which we call it accumulation-based modulation, is that this silicon and silicon separated by oxide will make a capacitor for you. By applying a voltage between them, you can easily accumulate charges. And that charge accumulation results in the modulation of silicon, changes in index of refraction. Conventionally, we put p-n junctions, and we need to inject carriers using a current. That results in power consumption. And this technique doesn't need technically any tangible power consumption because it's done in a capacitive way. So that's the name of the game. And of course, this shows the resonance wavelength of that resonator by applying a voltage. And you can see that because of the charges, it will cause a good shift. So this is a cartoon of the fabricated device. 2 layers of silicon separated by oxide, a waveguide, and a resonator. And of course, you need to do fabrication for pads and applying voltages to the 2 layers and so on. And these are SEMs of different portions of the device. And eventually, you generate means of putting those contacts, and this is what you get aesthetically. So you have this double layer structure, you apply a DC voltage, and then you monitor its resonance, and you're not surprised to see that the resonance wavelength shifts. But in order to see its high-speed performance, you need to put it into a high-speed setup. It's a very conventional setup. So you have a tunable laser as your source. You control its state of polarization and apply it to your device. Again, waveguide coupled to the resonator. And then you take the signal out, amplify it, necessary filtering is done, and then the signal goes into a photodetector, and it goes either to oscilloscope or a spectrum analyzer, and in some cases you do the bit error rate tester and so on. Very conventional high-speed setups. And this is the performance of that modulator. So you can see that this is the frequency of the applied signal, and this is the modulator response. And modulo some points here, this clearly shows better than 10 gigahertz response. This shows the applied sine wave, and this shows the I, which is very clean, up to 15 gigabit per second. A little bit more investigation. Our conclusion is that our characterization setup is the limit in getting to the end of the performance of such a simple modulator. But our assessment is that a simple modulator like that is a 10 dB modulation depth, 55 femtojoule per bit. Insertion loss is 5 dB, and bit rate is 30 gigabit per second. And such a system has a lot of room for improvement. So some of the improvements that we figured, and we are now working on it, is that this was published a few months ago, is that we did a doping all the way inside this 3-micron disk, and that adds capacitor. But if we remove the unnecessary regions where there is no doping needed for that, then we will definitely reduce the capacitance by a factor 2. So that increases the speed by a factor 2. Also, we can bring these regions closer to that end and reduce the size of that resonator. And estimate is that you can easily get into 100 gigabit per second modulation speed. And that's what we are shooting for. Now, one of the advantages of this structure is that it gives you a solution to fabrication imperfection almost for free. A major challenge in using resonators is that you fabricate a resonator to operate at a wavelength, but unfortunately, that resonator doesn't operate exactly at that wavelength because your fabrication accuracy is not up to nanometers. So now you have to do something called trimming, which means you have to come and apply a signal to bring it back for practical applications exactly to where it's supposed to. And in most cases, conventionally, people put a heater on top of that resonator and then apply a signal to just heat it up and correct it dynamically. This structure doesn't need any specific trimming because I can clearly and easily apply a DC voltage to inject enough carriers to bring the resonance wavelength to the operation point, and then have my AC signal on top of it applied. So it's no power consumption for trimming, and that's one of the major advantages of such a device. I'd like to also mention a fun experiment that can be done, something that we call field configurable devices using this technology. And for field configurable devices, what I mean is that we can provide a chip that has multiple resonators and waveguides, and the user can select the resonators that that he or she wants and remove the other resonators by just applying a voltage. Something similar to the field configurable gate arrays in microelectronics. Now, the way it works is simple. You apply a voltage to this double-layer silicon resonator that we talked about, and you change its resonance wavelength. However, if the voltage is large enough, in this case 44 volts for this very simple device, then what you do is you cause breakdown in the oxide between the two silicon layers and completely demolish the resonator. This is the SEM after breakdown, and this is getting into the silicon. You see it's completely damaged. It's not a resonator anymore. It doesn't have a good quality factor. So technically, the user can apply that amount of voltage to just kill any resonator that user doesn't want, and basically make the spectral response the way that the user wants. You can think of reconfigurable switches, reconfigurable spectrometers, and so on. And I don't use reconfigurable because it's a one-time configuration. I call it field configurable. And of course, for this case, in this simple, crude example, we use, I believe, 60 nanometer oxide in between. I can reduce that to smaller values, and then you can work with a few volts for that configuration. This is just one example. I don't go too much into it, but basically it's 2 inputs and 2 outputs and 2 resonators, and resonators do the job of routing. And depending on whether your resonator is on resonance or off resonance, or the resonator is killed or not killed, you can have an arrangement where each one of these inputs can go into each one of those outputs. And that's one of the applications that, again, we published, I believe, a couple of years ago for that. Let me just quickly wrap up by adding a couple of words. I assume I have to finish at 50 minutes. Is that right? So I have a few minutes. OK. So the idea that now we're going after is that, OK, we have platforms, both material-wise and device-wise, that now can allow us to go to the next step. And next step is to bring functionalities that silicon or silicon nitride don't have. And these are typically done by materials like polymers, graphene with very high speed because of its very low resistance and very high mobility, something that can give us very low RC time constants in our modulators. 2D materials and emerging material systems with amazing performances, having direct band gaps and so on, and phase change materials and so on and so forth. And this is what we envision as the future material system that use the backbones of silicon and silicon nitride and then combine them at locations where specific performances are needed, where polymers, graphene, 2D materials, and others can pitch in those performance measures. This is a recent work that we are still working on. This is a silicon nitride material platform with double-layer graphene modulator. So the idea is very similar to that double-layer silicon, a capacitor modulator. But the advantage of graphene is that its resistance is very low. Therefore, you can get a very small RC time constant and very high speed, easily above 100 gigabit per second. And these are the stage of fabrication. But the idea is that you can have silicon nitride as the base material, and you can have 2 layers of graphene separated by oxide, which in this case is aluminum oxide, fabricated by atomic layer deposition. And this is just to show that the opportunities are numerous when you have the concept of hybrid material systems. And let me just fabricate let me just complete the story and conclude that silicon photonics is now an accepted technology for making changes into the world of photonics, optoelectronics, with applications in sensing, in information processing, in RF signal processing, and many others where the speed of optics, the bandwidth of optics, can come to help the challenges of electronics. And with a lot of investment in this field, the field is now moving toward next generation devices where you don't need to just rely on silicon to give you all the measures and performances. Rather, you can form your material in a hybrid platform where different layers provide different material properties for the application that you need to make the devices with the performances that you require at different locations on the same chip. And that is the concept that hybrid material platforms can enable and is now enabling in integrated nanophotonics. Thank you for your attention.
Any questions? Lee, yeah.
It's very nice work, and I have two questions. First of all, to increase the response time of your silicon device, you use this differential mechanism, which is very clever, to achieve very fast rising and falling time. Can you do the same thing to the hybrid silicon nitride device? It's not straightforward to me. And the second question is that in your charge accumulation-based modulators, will these charge increase the absorbance of silicon due to free carrier absorption?
Okay, I guess I need to repeat the questions. The first question is that in the cases where thermal tuning is allowed and it provides the necessary timing, could we apply the same differential architecture to the silicon nitride platform? Well, the answer is yes. It's kind of independent of what is beneath the silicon layer, because silicon and silicon nitride devices are supposed to work together to make a general platform, but each one does its job separately because the signal is either in silicon or silicon nitride. It just adds challenges of fabrication because you need to make sure the heater is there, and then you apply the signal and so on and so forth. Fortunately, the heat does not adversely affect the silicon nitride response because silicon nitride has a much lower thermo-optic coefficient. So that's question one. Question number two was that in the case where we have double-layer silicon accumulation-based modulators, shown in this slide, but we are injecting carriers to change the index of refraction of silicon. Does this cause any loss in silicon because of free carrier absorption? And the answer is yes. In all cases where you inject carriers to change the index of refraction, you add some loss. But it depends on the size of your device, how much carrier you need to inject, and how much loss you can tolerate. It is not expected that these devices, these modulators, have 0 dB insertion loss. But these typical losses are usually manageable. Even commercial silicon photonic modulators use that, and they are not excessive if you just apply enough carriers to change the resonance wavelength.
Anand, yeah.
Thank you for the beautiful talk. I have two questions, both related to energy dissipation. In a number of slides, you talked about low power. So the first question is, I'm someone who does modeling of nanoscale devices. I'd like to know low with respect to what? With respect to what? That's the first question. The second question is, so in a lot of your slides, there are three major causes for energy loss. One is charging and discharging of capacitors. So there is a half CV square loss, just like in regular logic circuit design. Then there is a I square R loss because you're constantly pumping charge and taking it out. So there is a local conduction current in various parts of your silicon. So there's a I square R loss. And the third loss is the loss of the photon signal by itself. I was wondering if you could if I was going to teach this in a course, how would I apportion these three energy losses And is one of these three energy losses the dominant energy loss that future technology should work on?
Thank you very much. So the first question is that when we talk about low power devices, with respect to what, or what is low power? The way in optics we term power consumption, let's say for modulators, is the power consumption per bit modulation. So in other words, in this example that I mentioned, the number we suggest is 27 femtojoule per bit. That's the energy you have to provide. That's the electronic energy that you have to apply in order to do 1 bit modulation. And now, what is low? Well, to be honest, nothing is low. Sometimes femtojoule per bit was considered low power modulation. Nowadays, there is a MURI call for this year that is now, I think, being decided with the topic attojoules nanophotonics. So, the push is for attojoules. But if something is in the ballpark of a few tens of femtojoules per bit, this is what I really term it very low power modulation. The second question you raised that, okay, as far as energy loss is concerned in an energy platform, yes, we have two different facets for losing energy. One is the electronic energy per se, something that is related to the circuitry that supports that capacitor through the resistors. And then the other facet is optical loss, which are to a good degree related to each other, but two different means of managing. The way in optics we care about is that both of these are important, but from different perspectives. We separate optical energy loss from the electronic energy loss. For us, electronic energy loss is very important. It's very important because that results into all kind of heating and problems and so on. And for this type of devices, my feeling is that with proper design, 1/2 CV squared loss is the dominant loss. As far as the optics is concerned, well, modulators have losses, but we have multiple losses inside the system. Even the waveguide that carries the signal from point A to B has losses because of fabrication imperfections. And our measures is usually in the form of the so-called insertion loss. And that is fiber to fiber. So light comes from fiber into my optical chip, goes through that, is processed, and then goes back into the fiber. And what is a good measure for that? A few dB is acceptable as far as the optical loss is concerned. So the way people are pushing the low power operation in optoelectronics is as if they don't care much about the optical losses. They say, okay, I have it, let's just assume a couple of dB insertion loss is enough. But there is a lot to achieve in the electronic side, making the electronic circuitry, making the device architecture better and better to reduce that power because, in essence, femtojoule is not necessarily the sweet spot. In essence, there is no fundamental limit not to be able to achieve attojoules per bit. And a lot of effort is focused on that electronic loss reduction rather than the optical loss reduction. As if we in the optics community say, we have reduced the optical loss enough. In many proposals, in many highly competitive proposals, you don't even address reduction of the optical loss. You just mentioned that it is a well-known technique how to couple fiber into waveguide. This is a well-known technique how to reduce the insertion loss from input coupling and output coupling. And our fabrication, even with CMOS, is now at a good stage that losses are manageable. And therefore, you don't invest too much of your time and energy on reducing the optical losses. I hope at the level of classroom, I was able to give some comments on that.
So these things all are done kind of university clean room, or so are you guys looking into also foundry?
Well, the only piece that was not done in university, and that was a pain to do, was the ion implantation, because it requires multiple stages of ion implantation, like 4 or 5 stages. That's something we were not able to do at Georgia Tech because we didn't have facility. But we have really not looked into foundry yet because still we need to reduce some of the shortcomings, bring the speed up. Eventually, yes, we are looking into the possibility of testing it with foundry at some point.
Nitride is also like there to be in foundry, or is mostly silicon? Like
Well, this is all silicon. Like this multi-layer silicon is now silicon only. But I believe any foundry system, especially those that are coming out of this $200 million grant, would have nitride, silicon, 3.5s, even 2D materials, graphene. It should be, right? Otherwise, 200 million. I believe today you can easily get silicon and silicon nitride in places like IMEC and LETI and places like that.
Okay. So let's thank the speaker again. And